In this video, we're going to look at Dijkstra's algorithm. The algorithm finds the shortest path between any two vertices in a network. This algorithm differs from prims and crucicles, where we find a minimum spanning tree which connects all vertices. So Dijkstra's is looking for a shortest path rather than connecting all vertices. The term shortest path means of lowest weight. That might be distance, cost or time. We're going to look at some basic terminology and then go on to apply the algorithm. Let's start off with a network. A network is a weighted graph. So in this particular question, this is a network. We have vertices or nodes, so for example S, A, C, F, T, these are vertices, and then we have arcs or edges, which are these lines connecting the vertices. We're given the weight, so this might be time, it might be distance, it might be cost. So if we look at arc or edge SB, that has a weight of 6. In the question, we're asked to use Dijkstra's algorithm to find a shortest route, so shortest path from S to T in each of the following networks. So I've chosen this one right here. We're asked to show our working, and then we're asked to state our shortest route and their lengths. You should show how you obtained your shortest route from your labelled diagrams. So here is a network, and this is the typical template you'll be given to carry out Dijkstra's algorithm. Let's just consider this box right here. What we have now is a box here with 4 parts. This is the vertex. So this is vertex S, and that corresponds to our starting point. What we're looking for is the shortest route from S to T in the network. The second box is what we call the permanent label for the order. So for example, this will be my first box here, so I'm going to mark that as 1. The end box is what we call the final or permanent value, and that's the distance from S. The bottom box are our working values. So let's go ahead and look at applying the algorithm, and then I'll look at a more sort of general approach to this, or a more informal approach. The first step of Dijkstra's is to give the start vertex a final value of 0. So what I'm going to do is just start filling out the boxes. We're finding now a path of shortest weight from S to T. So this is going to be my first starting box. This now is what we call the permanent label. So this is the first vertex or first node now in my path. The distance we've covered is going to be 0. So if we're taking these to be distances, they might be meters, kilometers, the distance of S from S is 0. What we now do is find all of the vertices directly connected to this vertex. So once we've assigned a permanent label, we find all of the vertices directly connected and give them what we call a temporary label. The temporary label is our working value that goes in this box. What we're looking for are the directly connected vertices. So we can see from S to A we have a distance of 7. From S to D we have a distance of 16. And then from S to B we have a distance of 6. What we now do is choose the vertex of lowest weight, or the arc of lowest weight. I've got 7, I've got 16, or I've got 6. Quite clearly 6 is the lowest weight. I can't yet consider C, as that's not directly connected to S. So what I'm going to do is now state that this is going to be the second vertex. So this is my permanent label for now which vertex this is in the shortest path, and the distance away from S is going to be 6 units. Now at this stage what I need to do is continue with this process. I can see that this has opened up other options. I've now given this a permanent label. I've got it now as vertex 2 at a distance of 6 units. What I'm looking to do is better my original distance. So let's see which vertices are connected directly from B. Quite clearly we don't want to go back to S. We've got a choice of D and we've got E. So it's D or E directly connected from B. We saw from S to D was 16. we can now see that from B to D is going to be 8. 6 plus 8 beats the 16, therefore we put the 16 in brackets and we've got now a new working value. We want this to be as low as possible. So 6 plus 8 is 14. So the shortest distance, or the shortest path from S to D is actually S to B to D currently. It used to look like it was 16, but what I've done now is found a quicker route. So in our working box, we then change that. We're always looking to better our working value, and we show it's bettered by putting it in brackets and writing the new lowest weight next to it. Let's also look now at the connected node or vertex from B, and that's E. So we've got now 6, the distance from S to B was 6, and now we've got an additional 3. So the quickest route currently from S to E is going to be 9 units, and I put that in my working box. So these are my working values or temporary labels. This is a permanent label, this is a permanent label, this is a temporary label. I've now got the choice to connect up either A, which has a weight of 7, D, which has a weight of 14, or E, which has a weight of 9. I'm looking for the lowest value. Quite clearly, that's going to be 7. So if B was 2, A is going to be 3. I give that the permanent label. That's now vertex number 3, and that has a distance now of 7. So we're taking these to be distances of a weight of 7. So S to A is 7. Now, I can see that I can connect directly from A to C, which is going to be an additional 10 units. So at the moment, my quickest or shortest path is going to be 17 units. I've assigned a temporary label. The top row are permanent, the bottom row are temporary. Now we thought we had found a better route from S to D. So we went S to D, which was 16. Then we saw that we could actually get there from S to B to D, which was 14. I can now see that I can actually get there even quicker or an even shorter path. 7 plus 5 is 12. Therefore, we need to show that we no longer want the 14. There's a quicker or shorter path, and that's going to be 12 units. So I now consider everything that's connected up with something that's not connected and look for the lowest weight. So we've assigned the permanent labels here. We've now got a choice of C, which is 17, D, which is 12, or E, which is 9. E, being 9, is the lowest, so this is going to be the fourth vertex now that we're going to add to our shortest path. We give it now the permanent label, so the distance now, the shortest distance from S to E is 9 units. Okay, those unconnected now to the ones that are connected. So we can see E to G, I need to add 6. So I'm going to make this now 15. That currently is my best option. So if I wanted to go from S to G, my current best option is S now to S to B, then we've got now B to E, and then E to G at 15 units. I can connect up E to H. 9 plus 4 is going to be now 13. Now you might say, well, could I connect this one up to this one? It would give us a higher weight, but we've not yet given this a permanent label. This still has temporary working values. So let's go ahead and consider all of the vertices that are not yet connected or in the shortest path with those that are. I've got now 12, I've got 17, I've got 15, I've got 13. 12 is the lowest weight, therefore this becomes the fifth one. That becomes 5. We now give it a permanent label of 12. So 12 units, 12 kilometres, 12 metres, 12 miles, whatever it is, that is now the lowest weight we had on offer. Now let's consider our connections. We can see that D can be directly connected to C. I don't want to go back to A, don't want to go back to B, don't want to go back to S. So we can see that 12 plus 4 is 16. So 17 is no longer the shortest distance, and we can swap that with 16. Often you see these being crossed out. I like to keep them in brackets, as I just think crossing out, if you've made an error, it's often harder to work where you've gone wrong. Also, you may see people consider now, for example, and we'll look at it on this one, put in now 18 here in brackets. Check with the exam board, check with your teacher. I generally don't like to put the 18 here now because it doesn't beat 15. I'm looking for the lowest weight. So just ask your teacher what their general preference is, or check some past papers just to ensure that that notation is not being used. So we can see now that 16 is now the shortest distance here, and or lowest weight. Now I'm not going to add the 18 here because it doesn't beat the 15 that I've already found. So let's go ahead and consider now all of the unconnected vertices and the direct routes. I've got H at 13, I've got G at 15, I've got C at 16. 13 is my best option, and that becomes now number 6. Permanent label assigned. The permanent label now of 13 is the shortest path from S to H, and this now becomes the 6th vertex. Okay, we can see now all of the unconnected vertices from H can now be given a temporary label. 13 plus 1 is 14, therefore we can beat now the 15, and I'm going to swap that for 14. We can see now that 13 plus 10 will give me 23, so at the moment, what I'm looking to do, remember in the question, the shortest route from S to T, so currently my shortest route is 23 units. So they're the only ones that I can connect. I don't want to go back here as we've already connected that one up. So I've got now 14, I've got now 23, and I've got 16. So let's go ahead and see which is the lowest. The lowest out of 14, 16 and 23 is going to be 14. Therefore, this is going to be 7. This is given a permanent label of 14 units. That is the shortest distance from S to G in the network. Okay, let's look now at the unconnected vertices with the connected ones. It often throws students that going backwards here is a good idea, but we can see, although it looks like we're getting no closer, remember these weights are not now relative to their size. They're not, for example, this is meant to be 1 unit, yet this is 8. So do check. So we can see now 14 plus 1, we can beat that. So our new lowest weight, or our temporary working value, has gone from 17, 16 to 15. We can see now that I can go in this direction here to T with 8. So I'm going to look at 8 now, and we can say, well, actually, that's better. 14 plus 8 is 22. So I've now got a shortest distance from S to T of a working value of 22. So let's go ahead and look now. There aren't any others that I want to do. Everything else has been assigned a permanent label. I have a choice of going to C, I have a choice of going to T. So let's see what we've got. We've got now a choice here of 15, or we've got a choice of 22. 15 is lower, this becomes 8. We assign a permanent label of 15. Okay, from here, what can I connect up? Well, the only thing left now is this one right here, and that's going to be a working value or a temporary label of 18 units. So let's see what I've got the choice of. I've got nothing else to choose from. I've got now 18 or 22, so we're going to say that this is number 9, and we can assign a permanent label or now the final value of 18 units. If I consider what I can connect up from F, the only choice is T. 18 plus 2 is going to now better that, and that will give me now a weight or distance of 20. This is the final vertex. All I need to do is label this up 10, and we have now a weight of 20 units. So there we go. We've found now the shortest path from S to T. Often you'll be asked to state the shortest route and the length of the shortest route. And that's what we're going to do now. Let's first look at now the steps of Dijkstra's algorithm. What we do is start with the given vertex in the question. We give this now a permanent label of 0. This is the distance away from S. This is the order of labelling, so this is the first vertex. We then consider all vertices that are directly connected. A is, D is, and B is. C is not, E is not. We look for the lowest weight. When we found that in our temporary labelling, we give it a permanent label, and this now is the shortest distance of the vertex from our starting point. We then label them up. So the first vertex was S, the second one was B, the third one was A, the fourth one was E. They're quite clearly not always going to go in alphabetical order. Once we have a connected vertex with a permanent label, we consider all of the unconnected vertices from that particular vertex or node. We then see if we can better the original distance, and we give the original distance brackets and work out a new one. If it doesn't have an original distance, we simply calculate the shortest path. We complete this process right up until the end vertex or node, and you can see that I've done that up to T. Now, what we need to do at this stage is find the shortest route, and we work backwards. So let's consider, how did I get from S to T? Going forward is haphazard, going backwards is significantly easier. So I've started here with 20. If I've gone this way, then if I consider now this value minus this value, we should get this one. Quite clearly, 20 minus 13 is not 10. I didn't go back that way. Or if you like, if this was 20, if it was 10, I'd end up with 10. And here, 20 minus 8 is not 14. Or if you like, 20 minus 14 is not 8. That would generally be seen as a more, probably the better approach, 20 minus 14. So we're looking at these permanent labels. We can see clearly that it's going to be the 18. 20 minus 18 is 2, so we can see that we've come back this way. Now, the way I like to do this is to work it backwards. So what we've got here now is T. Then we're going from T to F, and I'm going backwards on this. So we consider now that we're going from, because we're going to start here with S. Now let's have a look. Quite clearly, our only choice from this point now is to go to C. We can see 18 minus 15 is 3, or if we add 3 to 15, we get 18. In terms of these shortest paths, there might often be more than one shortest path, and you will be asked to state different shortest paths. In later videos, we will look at that issue. So let's do that. We're going to now go back to C. So that goes to C. If I now consider where I'm going, it looks like we should be going here, or we should be going here. 15 minus 7 is not 10. 15 minus 12 is not 4. 15 minus 14 is 1. Therefore, we're actually going to G. And as counterintuitive as that seems, it's fairly logical. So we're coming back this way. Now, let's see where we've gone from here. 14 minus 12 is not 6. 14 minus 9 is not 6. 14 minus 13 is 1. Therefore, we're going to H. So we're going to H. From here, our choice now is pretty limited. We can see that we're going to go to E. 13 minus 9 is 4, or 4 taken from 13 is 9, and that gives us now E. At this stage, we can see the only route back is to B, and then from here we can see that the route back is to S. So my route now is S, B, E, H, G, C, F and T, and the length of the shortest route is 20 units. We weren't given anything, so I'll put 20 units. It might be kilometres, it might be metres, it might be miles. So we are asked to use Dijkstra's algorithm to find a shortest route from S to T in each of the following networks. So this is a network. A network is a weighted graph, and we can see the weights on each of these. We need to show our working. This is our working with our boxes. Often in the exam, you'll be told what these boxes mean, and if you do, use it. So this now is the vertex, so vertex C. This is the order of labelling. This is the permanent or final value, or work of the final distance from S, and then this is our working values or temporary values. Permanent along the top, temporary down the bottom. So there we go. That is an application of Dijkstra's algorithm. You might not be asked in a question to go from S to T. You might be asked to go from S to G, and that would be perfectly fine. The lowest weight from S to G would be 14, and then we'd simply work out how we did that. And we can see that that's actually in the shortest route. But for example, if we were given D and we were asked to find the shortest route from S to D, we would say that that is going to be 12 units, and we would work out how we got there. And we can see that that would be now going back to A and back to S. Often in questions you'll be told that one of these routes or roads is closed and to work it out. And again, we'll look at that in a later video.